Okay, this is lesson 3.1, statements and quantifiers. And so we're going to, this is the first lesson in MAT134. Okay, we're going to go over distinguishing the objectives, distinguishing between statements and non-statements, compose negations of a statement, translate between words and symbols, interpret statements with quantifiers and form their negation, find truth values of statements involving quantifiers and number sets. Okay, a statement is defined as a declarative, meaning like we declare it either true or false, but not both at the same time. Okay, so basically, when we talk about a statement, we're talking about something that, like, the sky is blue. That's either true or it's false. Whereas I like blue skies, that's an opinion. That is not a statement. Okay, so a compound statement may be formed by combining two or more statements, making up a compound statement. And they're connected by and or not if then statements. So if we're looking at, let's go to the board. Okay, so we're talking about a statement and then a connective and then a statement. And this statement can either be true or false on either sides. Connective, we're going to use and or not, if then statements. Okay, so if we were to say something like the sky is blue, or the dog ran. Okay, this is a true statement, true or false statement. This is a connective. This is a true or false statement. So that would be considered a compound statement. But one other thing, you could also include an equal to sign or a not equal to sign in there. Okay, for a compound statement. Okay, so let's go back to our notes. And so all right, so if we have here decide whether each statement is a compound statement, you can pay me now or you can pay me later. You can pay me now or you cannot pay me now. You can pay me now, that's true or false. Or you cannot pay me now. Or you can pay me later, that's also true or false. However, so that's considered a statement. My pistol was made by Smith & Wesson. That is not a compound statement because Smith is not true or false. Wesson is not. In other words, Smith & Wesson is a name. It's not a statement, connective, and statement. So the second one is not a compound statement. Okay. The sentence, Max has a valuable card The negation is the opposite of that. Matt does not have a valuable card. So if we were to say the moon is made from green cheese, let's say, then the negation to that would be the moon is not made of green cheese. Okay. Form a negation for each statement. That city has a mayor. So if the city has a mayor, so the negation to that would be the city has not a mayor or does not have a mayor. The moon is not a planet, so the negation to that is the moon is a planet. You take away the not. So it's the opposite of the true or false statement. Okay, use the following inequalities here. And so if we were to, so we have A is less than B. The smaller end of the inequality sign is the lesser end. A is greater than B. So here B is on the smaller end of the inequality. A is less than or equal to B. A is greater than or equal to B. So if we have, let's look at a problem. So let's go back to our board. And so here we have a statement. And the negation. So if we were to use statement and negation in terms of inequality, if we have A is greater than B, then the negation would be A is less than or equal to B. So now if C is less than or equal to D, then is the statement, then the negation would be C is greater than D. In other words, if the original statement does not have an inequality sign, you're going to flip the inequality sign and then you're going to put that equal to sign in it for the negation. If the statement has an inequality, has an equal to sign in it, you flip the inequality and you take the equal sign out. Okay, so if we were to look at the problem x is less than 9, okay, the negation would be x is what? You should have said greater than or equal to 9. Okay, B, here we have 3x minus 2y is greater than 12. So this whole first part is one statement, okay? One is a statement. So that doesn't change. It's still going to be 3x minus 2y, and you have 12. So the only thing that's going to change is the inequality sign. So what is that inequality sign going to be now? You should have said less than or equal to 12. Okay? Alrighty. Okay, so let's take a look at More PowerPoint notes. Okay, symbols. To simplify work with logic, we use symbols. P and Q are the most common, sometimes R, sometimes S, but mostly we use P and Q. The connective and is a rooftop looking symbol, and that's a conjunction. So and means both. Or means one or the other, right? So that's going to be a V looking symbol, and that's a disjunction. Not, you have this tilde looking symbol, and that's a negation. Okay, so back up. All right, so let's take a look at another problem. Okay, so we'll put this on slide mode so we don't see the answer right away. Okay, let P represent it's raining and Q represents it is March. Write each symbolic statement in words. Okay, so we're going to use P or Q and then not P and Q in parentheses. Okay, so let's take a look at the board and let's see how we're going to do that. Alrighty. Okay, so first thing I like to do is write P, it is raining. It is raining. And Q, it is March. It is March. Okay, so we're looking at the problem P or Q. So we would say here, since P is it is raining, we would put it is raining. The V looking symbol means or, and then Q is equivalent to it is March. And there we go, we've converted our symbolic statement into words. Okay, so let's say that was A. All right, so now let's look at problem B. Here we have not, and in parentheses, P, actually, I want to do something before that. I'm going to add a problem. So let's say we say P and not Q. Or let's do this. Better yet, not P and Q. Okay. So not P and not Q. So we're saying here it is not raining. It is not raining. It is not raining. And it is not March. Okay. All right. So I added that in. All right. So now problem B is not P and Q. Now this is different from this because this would be it is not the case that it is raining and it is March. In other words, it's not like you can distribute that not into both and get this, because the truth tables do not, these are not equivalent truth tables. And you'll see that later on in the lesson. Okay, so this is a little bit different. So anytime you see that till the outside of the parentheses, you're going to use it is not the case. Okay, and it's just when the not symbol is outside of the parentheses, because first you're applying what's inside the parentheses first, P and Q. So P and Q, let's say, are true. Then the not symbol would make it false. So we're saying it is raining and it is March, but it is not. But that's not, correct in how it's written. So you have to say it is not the case that it is raining and it is March. Okay. All right. So let's move on with that. Okay. All right. So the words, quantifiers, the words all, each, every, and no or none are called universal quantifiers, which words or phrases such as some, there exists, for, at least one, are all called existential quantifiers. So in other words, we could say the quantifiers are absolutes. Okay, so for example, all, the statement all do, that's an absolute. That's an absolute. Whereas some do not, that's a negation. That is not an absolute. All versus some. So some do is a statement. That's not an absolute. None do. So you're going from not absolute to absolute. Some to none. Whereas before you're going absolute all to some. So you're either going all or none. All or some or none. So it's always an absolute. The negation is not an absolute. Okay. So if we were to look at let's say another example to add to this would be no do, some do, or some do, none, no, or some do, all do for the statement and quantifier. Okay, so okay, so let's move on and put this back on. Okay, for the negation, form the negation of each statement. Some cats have fleas. Here's that some. So you want to change that from some cats have fleas, since there's already some there, right? Then no cats have fleas would be the negation. So for some is an odd absolute. No is an absolute. I mean, there is none. So now you have some again, right? Some cats do not have fleas. So here you're saying some do not, so the negation to that would be all cats have fleas. So you went from some to all, because here we're saying some do not, so now we're saying all do. No cats have fleas, so what would be the negation to that? You should have said some cats have fleas. Okay. All right, so now let's look at number sets. Natural numbers, when we count starting with 1. We don't start with 0. So natural numbers are known as counting numbers. Whole numbers are the same thing, but there's a 0 in there also. That's the only difference between a whole number and a natural number, is whole numbers have 0 and natural numbers do not. Integers, positive and negative whole numbers, right? Okay. Rational numbers, basically rational numbers are fractions, where you have an integer p over integer q. And so they're a fraction. But as a decimal, they can either end like 1/4 or 1/2. 1/2 comes out to be 0.5, 1/4 comes out to be 0.25. Or it can be repeating, like 1/3 is 0.33333. Okay, so rational numbers are either fractions or they are decimals that end or repeat. Okay, next, irrational numbers. Irrational numbers do not, their decimals do not end and they do not repeat. There's no pattern to the decimal. Also, irrational numbers tend to be radical numbers. Pi is irrational, 3.14159, it goes on and on and on. Okay, so, and then real numbers are all these other numbers put together. Everything, real numbers are everything. The only thing that is not a real number is imaginary numbers that have I in it. Imaginary or compound numbers. Okay, so let's look at this next problem. Decide whether each of the following statements about the sets of numbers is true or false. There exists a whole number that is not a natural number. So do we have a whole number, any whole numbers that are not natural numbers? You should have said 0. 0 is a whole number that is not a natural number. So that would be a true statement. Okay, every integer is a natural number. Well, if we look at integers, right, every integer is a whole number? No, because we've got negatives. So that's false. And it only takes one number to make the whole thing false. So notice they only looked at -1. They didn't even go any further than that. Okay, and that is the very first lesson for MAT134. And thank you very much. Let me know if you have any questions, and have an amazing day.